this idea of limits. There are two kind of real major preliminary concepts that you need to have for calculus when you step into calculus. One is about what we just did, about that sigma notation, that being able to find the sum of things. And as it turns out, finding a sum not only of a finite number of things, but of an infinite number of things. For example, if I said 3.5, and well, let me just start off easy. Let's start at 3. If I said 3, I'm going to add a number to that. I'm going to add 0.5 to that. So if I added 3 to that, I get 3.5. Now, I'm going to add an infinite number of numbers to this. I'm going to add an infinite number of numbers. And you would think that if I keep adding numbers forever, that this number should grow huge, and that the sum of these numbers should approach infinity, right? If I'm adding an infinite number of numbers. Well, the next number I'm going to add is 0.05. So if I add 0.05 to this number, I get that. Now the next number I'm going to add is 0.005. Well, if I add 0.005 to this, I would get that. If I add, the next number is 0.0005, I'm going to get this. And if I keep doing that pattern, and keep adding and adding and adding and adding numbers, even though I'm adding an infinite number of numbers, do you see that this number will never get bigger than 3.6? So adding an infinite number of numbers, you can actually have a sum that is an actual number. And that concept, even though that may seem a little kind of out there, is kind of a big deal in some of the things we think about and talk about in calculus. So, limit. What is a limit? What do we do with it? On your calculator, get this picture. Plain old y equals x squared. And take a look at the graph. Try to do a nice little simple window. Do the zoom standard. And look at that parabola. Isn't it pretty? This is x squared minus 6. Minus x minus 6, sorry. Now go to the table. The table is above the graph button. So go second graph and look at the table. Wow. And you see a bunch of numbers there, right? It shows you all the values at different points on the graph. Notice what happens as at 4. The value at 4 happens to be 6. Now I want to change the table a little bit. Notice above the window button, it says Table Set. So above the window button, go to Second Table Set, and we're going to change the way the table works. Change the table set start to 3.7. And then what's this little notation here mean? Delta. Which means change in. It's the Greek letter delta, D, for difference, or the change in. So we're going to make the change in the table 0.1. And then go back to the table again, and you should see something like that at the top. You go back to table. We all good? Okay. So here's the thing I want you to see. Limit. The idea of a limit is not what's going on at the point. At 4, this graph is equal to 6. At 4, this graph is equal to 6. But what I'm interested in is not what's going on at 4. I'm interested in what's going on near 4. Look what happens as I start getting closer and closer to 4. As I start getting closer and closer to 4, look at the answers. They start getting closer and closer to 6. And as I get closer and closer to 4 from the other side, it starts getting closer and closer to 6. Now the fact that at 4 it's equal to 6, I don't care. Limit, I'm going to say this a bunch. Limit is about what happens near the point, not at the point. Graphically, what's going on is as x gets closer and closer to 4, the answer gets closer and closer to 6. Different equation. Go back in and change your equation to this one. And we're going to look at a different point. So it's the same initial equation, but put parentheses around it, and then divide it by x minus 3. And then get a nice little pretty window of it. And it's going to be, you got it squared in there, right? So you're going to get some kind of curvy thing going on. X divided by x minus 3, the whole thing, yeah. And you get some kind of little curvy thing? Huh. Any of you get a straight line?
Yes.
Well, how in the world could that possibly be? Now do the same table thing. Let's take a look at what's going on near 3, though, in this case. As I get closer and closer to 3, sure enough, it's a straight line when I graph it too. But look what it says is happening at 3. You're getting an error. Now go back to first quarter when we did graphing of rational functions. The reason you're getting an error is because when I put 3 into this, I get 0. When I put 3 into that, I get 0. And 0 over 0 is undefined. That's not equal to 1. Division by 0, your house blows up. Sorry about that. Go home and you'll have your house will be all blown up. It'll be very sad. So, at 3, this function's undefined. But the idea of limit is not what's happening at the point, it's what's happening near the point. So as I get closer and closer and closer to 3, what's the y value getting closer and closer to? Look at it. 5. And as I get closer to 3 this way, although you can't see quite so much of it, it's coming down to 5. Does it ever actually equal 5? But the limit is still there. The limit exists. When it comes to evaluating a limit, listen to that vocab. I will ask you in a test or quiz to evaluate these limits. And when you evaluate a limit, you simply are asking, what's the graph doing? As x gets closer and closer to 3, what's the y value doing? That's what that means. In this problem, if I try to see what's going on at 3, if I plug 3 into this, I get 0 over 0. And that's your clue. There has to be some other way to do this problem. And as it turns out, this numerator factors like this. And the x minus 3's cancel each other out. In order to do this process for limits, you must be able to factor. Have I mentioned factoring before? We haven't had a Friday quiz in a while. We maybe need to get back into the swing of that and practice some more factoring again. But look what happens. After these guys cancel out, now I can take and plug in 3. When it comes to evaluating a limit, just plug the number in. If I wanted to know what the limit was at 5, I could just plug 5 in and see what I get. Of course, the more interesting questions are the ones where you can't just plug the number in. But try. Sometimes the more easy ones are just plug the number in and see what you get. Like the very, very first one I gave us without the denominator, just plug the number in, see what you get. Here's the definition of a limit. Jot that down. So what we did a minute ago was to take and say what happens as x gets closer and closer and closer to 3. So as x gets closer and closer to 3, then the answer got closer and closer to 5. And so we say that 5 is the limit of that function we just had, that x squared minus x minus 6 over x minus 3. 5 is the limit as x approaches 3. Even though at 3, it's undefined. There still is an answer to the limit, the number you're getting closer to. The notation looks like this. So that whole blue sentence looks like that in math. That's the equivalent mathematical sentence to that blue English sentence. So the problem we just did would look like this. The limit as x approaches 4 of x squared minus, well, this is not the one we just did, the first one we did, sorry. The limit as x approaches 4 of x squared minus x minus 6 is 6. That's the value it got closer and closer and closer to. The one we just did with the thing in the denominator, so that would have been read, we would say the limit as x approaches 3 of x squared minus x minus 6 over x minus 3 equals, and this got closer and closer to 5. Even though when you plugged in 3, it was undefined. When you plug a number in, and that's how you should always try to find a limit, often it won't work, but that's the first kind of logical, easy way to try. But if you plug in a number and you get 0 over 0, that's your clue that what we just did about how we factored, you should try that. Find something that'll factor and cancel out. And that's how you can find a lot of these limits. Something's going to cancel up here, and then you can plug in the number. Graph this one on your calculator real fast. And what you're going to see is something going on at -2. Because I would try to plug 2 in. I said -2, sorry. You're going to see something going on at +2. When I plug 2 into that, I get 1 over 0, but this thing's undefined. And it should look something kind of like that. What's that called, by the way, at 2? There's an asymptote at 2. But now look at what's going on as you approach 2. Now, I don't know if you caught this or not, but when we were doing the table, I talked about coming down to the number, coming up to the number from both sides. And a lot of time what you'll do is this kind of a notation. A limit actually is what's called a two-sided limit. You come to the number from both sides. But sometimes it makes sense to look at, okay, just what's happening from one side. So this notation, by putting this little minus up here, what that says is get closer and closer to 2, but get closer from only the left-hand side, the negative side. So as I get closer and closer to 2 from the negative side, what's this graph doing? It's going to... Where's it going? What's the y value doing? Going to -infinity. And so the answer to this would be -infinity. Now, -infinity is not a number. And so technically, this does not exist. But a way of showing that it doesn't exist is to write -infinity. And if I change this minus to a plus, now I'm approaching 2 from the right-hand side, and now this graph is approaching infinity, which again is not a number, and so it doesn't exist. So this graph doesn't exist at, or I'm sorry, this limit doesn't exist at 2. So the short answer is, what's the limit? It doesn't exist. All right, last little concept. We're going to go through this one kind of quickly, just so we can kind of see it and hear it. So continuity is a major concept in calculus. You'll see a lot of problems that start off and say, there's a continuous function such that blah, 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 blah. And continuity, 3 things have to be true. First thing has to be true is that the function has to exist at a point. So if I say, is this graph continuous? At 5. The problem we did where there was a denominator, that graph wasn't continuous at 3 because f of 3 didn't exist. The second thing that has to be true to be continuous is the limit has to exist. And then the third thing that has to be true is those 2 things have to be equal to each other. Now, I'm going to put this up on the next page, so this will still be here. In this picture, what I want to do is look at all of these points and see why this graph is not continuous. Now, continuity actually is really simple. What it simply means is, if you have a graph, can you start from the left-hand side and draw all the way to the right-hand side without picking up your pencil? Well, this graph up here, I can't do that. There's places where it's discontinuous or not continuous. So at number 1, let me run through these list of things up here. So does f of a exist? Well, there's a hole right there. So f of a doesn't exist. Is this graph continuous at a? No. because f of a doesn't exist. Look at b. Does f of b exist? Yeah, there's an answer. It's right here. I don't know what that answer is, but it's an answer. It's like the millionth customer is cheaper, you know? Does the limit exist? As I get closer and closer to b, am I getting closer and closer to the same value from the left and the right? And you are. You're getting closer and closer to, let me call this 3, let's say that's 4. You're getting closer and closer to 4 from the left and the right, even though at the point, there's no answer. Well, the answer is actually down here. But look at number 3. So at b, the actual answer is 3, but the limit is 4. So does the function value equal the limit? Therefore, it's not continuous. The function's not continuous there. Look at c. Does f of c exist? Yeah, the answer is up here. Does the limit exist? From the left and the right, are you approaching the same number? Say no. Look, this from the left side, you're approaching 3. From the right side, you're approaching 5. Does the limit exist? No. You have to be approaching the same number from the left and the right. So is it continuous at c? No, because the limit doesn't exist. Look at d. Does f of d exist? Yeah, there's the answer. 4-ish. As you approach d from the right and from the left, are you approaching the same value? Yeah, you're approaching that value. And does the value that the graph approaches, the limit, does that equal the actual answer at that point? Yes. And therefore, it's continuous at d. We'll play around with that a lot more later on. But that's the notion at each of those points. So f of x is continuous at a point if and only if all 3 of those 3 things are true. The function has to exist at the point, the limit has to exist at that point, and those 2 things are equal to each other. So that green list you just wrote down a minute ago, all 3 of those have to be true. So when I say on a test or quiz, is a graph continuous at a point, you would need to show all 3 of those. You would say f of 2 is equal to 5. The limit as f approaches 2 is equal to 5. And the limit is equal to the function value. Therefore, the graph's continuous. That'll be what our homework is then.